So my goals for today are that you guys walk away understanding the basic concepts of speech recognition models, that you know how to build a speech recognition model, and that you be able to adapt it so that it actually recognizes your own name. Okay. So what is the problem with names in jargon, and why are they difficult? Well, so my name is Etienne. That doesn't get recognized. I bet a lot of your names don't get recognized either. It's the same with the names of companies and the names of products. So there's two sort of essential problems. One is, of course, like that vocabulary represents a lot of words. There's tens of thousands of personal names, same with company names, same with product names. So that's a large vocabulary. The other problem is that the probability of occurrence of these words is very low unless you have additional context to know that these kinds of names might be coming up in a conversation. So the solution we've opted for is domain adaptation. So we do our own speech recognition in-house. When we look at our customers' own calls, our transcription is actually as good as Google's in terms of accuracy, and it's better than the other top ASR providers that we looked at. So this is a held-out test set of our own customers' calls where we had the advantages of domain adaptation. When we look at keywords, we do even better. And so what kind of keywords am I talking about? I'm talking, again, about the names of people, customers, products, or words that would be important for analytics. And so the reason these are important is, number one, user experience. People want their names and their company's names to come up correctly. And number two is analytics. So what we do is sales analytics, customer support, and then sort of enterprise business level analytics. One example would be we actually have right now a product in the call center where we show the real-time sentiment of a support call, and we're working on pairing that with the product entities so that people can understand, are my customers talking positively or negatively about my different products? And so getting the names of those products is a really important part of the pipeline to be able to do these kinds of analytics. All right. So in order to talk about speech recognition, I have to introduce a few concepts. So one is the lexicon. So what is the lexicon and what problem does it solve? Well, the problem is that letters are acoustically ambiguous. So for example, the word eager, right? The first E rhymes with B, the second E rhymes with So the letters alone don't allow you to know what the word sounds like, which to humans, that's okay because we learn. But to an algorithm, it's something we have to take into account. So the solution is that the lexicon is a pronunciation dictionary. It is also, incidentally, the set of allowable output words for the model. So if we want to add more words, we're going to have to add them to the lexicon. That'll come in useful later. So here's an example from our lexicon. So Uber Conference is one of my company's products. And on the right, that's the phonemic description of that word. So phonemes are a code that actually acoustically spells out what a word sounds like. And there's no ambiguity that way. Or I should say little ambiguity. OK, so now we can move on to the fundamental equation of speech recognition. I know this isn't a math audience. It's a lot of engineers here, not data scientists. So I'll do my best. Please, we can take questions after if there are some. So the magenta equation, that's the fundamental equation of speech recognition. But before we jump into that, I find it useful to say why the one above it is actually wrong. So sort of the naive misconception. So what is the goal of speech recognition? Provided an input sound, I want to know the words that were spoken, right? So output words, that's my output. It's not equal to the word sequence which is most likely. That would be that first equation. Argmax means the sequence that maximizes the probability of the words. And why is that incorrect? Well, those would be words like, okay, yeah. Those are the most likely words. And if people are kind of shuffling papers around and your microphone's on, you're doing speech recognition, you get those types of words to appear. But as soon as you start speaking, that's actually what you want to model, right? So the correct equation is looking for the argmax of the probability of the words given the sound. So the important thing is to condition the probability on the speech that was spoken. From there, we can change things around a little bit. With Bayes' rule, just moving things around. The reason we're going to do that is because it'll allow us to create some tractable models, and you'll see that below. So Bayes' rule, if people aren't familiar with it, is something you can look up after, but essentially allows me to switch words and sounds in the probability, and then I have to multiply by words so that it's still valid. And that will be a more convenient order. And now I'm going to do one more operation, and I'm going to break up probability of sound, condition on words, is going to become the product of a few expressions. I'm going to look, and each of these expressions corresponds to a different model. And so this will become very concrete with these different models. The acoustic model takes sound features as input, and it outputs phonemes. And so its job is to model the probability of the sound given phonemes. The lexicon takes phonemes as input and outputs words. And so its job is to give it the probability of the phonemes given the words. And then finally, the language model, its job is to give us the probability of a sequence of words. And so the way we represent these is actually using WFSTs. So FST means finite state transducer, and it's a kind of graph. The W stands for weighted, and the weights are essentially the probabilities of the transitions in the graph being represented. What this enables us to do is to represent each of these free models as a WFST and compose them in order to get that multiplication between these free probabilities. So if I can build a good one of each of these component models well and fine-tune them separately, I can then compose them, and that's going to do this multiplication. What it means in the end is that I can compare a multitude of sequences of words and know which ones are actually maximizing the probability of the sound, and then it will pick the most likely one. So I'll give you an overview of the domain adaptation process, and then we'll dive into some details, look at a little bit of code. So the first step is going to be to install Kaldi. So Kaldi is an open source speech recognition toolkit. It's state-of-the-art, gets excellent results. It has a large user community. So that's something that we use and that we recommend. You can download some pre-trained component models from Kaldi. Then you're going to have to compose the model in the way I described in the previous slide, the three models together. And then you're going to be able to decode. So decode means transcribing, so give it an audio file, and you're going to see what was spoken. And you could stop there. You could put it inside of an API, make a service into it, do all kinds of useful things. Once you do that, you have a speech recognition model. If you want to go one step further and get the names of your products or your own name to be recognized correctly, you can adapt the lexicon. You're also going to need to adapt the language model, and then you can recompose the models together and redecode the audio, and now you're going to get better results. And finally, if there's time, I'm going to talk about using grapheme to phoneme to infer word pronunciations at scale. All right. So this is the part where we make it concrete and look at a little bit of code. The first step, like I said, installing Kaldi. This is actually very simple. It's some Git clone, running some make files, installing OpenFST. We're going to download some pre-trained models. It's a wget command, so this part's easily accessible. Step 2 is composing the model. So that's actually where you're going to run a set of configuration files, and then the composition happens in the last line there. So there you're going to run make graph, and it's going to grab the component models and turn them into one big model. And the next step is going to be decoding. So you can create a test audio file. So our application is audio telephony, and that's what Dialpad does, right? Your application may be different. So it's going to be important for you to identify your application and select a test audio file that matches that application. And the sampling rate in particular should be consistent across your training set, your test set, your entire application. So you can use f of MPEG to downsample at 8 kilohertz. You set your path and environment variables, and you run your decoder of the online two-wave and NetLegend faster command. And those are hyperparameters, not the only set of hyperparameters that we use, but should be a good starting point for many applications. Okay, so now you've done it. Like, you've got a speech recognition model working. The next step is going to be adapting the lexicon, which again, that's the pronunciation dictionary. So a lexicon isn't provided in Kaldi, so we suggest using the CMU dictionary lexicon. So you can use wget to get it, change its name so that it's actually called lexicon.txt. And then, so my example is the word cranky with a K, that wouldn't be in a normal dictionary, right? So you need to add it to the lexicon. And so notice you need to actually know, is this a laser pointer? Yeah, there is. So you need to come up with the pronunciation of the word. So, phonemic vocabularies are not known to everybody, right? But there's an easy way to get this one, which is you look up Kranky with a C in the same dictionary, and of course it's the same pronunciation. And in my experience, by looking at other words, you can always figure out what the right pronunciations are. And there may be multiple ones, right? Tomato, tomato. You can have multiple lines per word in the pronunciation dictionary. Okay, so that's adapting the lexicon, that's done. Now adapting the language model. So I'm going to tell you what I'm going to remind you what the role is. The language model models the probability of a sequence of words. I see a smile, so somebody's already seen this one, I think. So the problem that it solves, the language model, is actually ambiguous speech. So if I say, have a great week, I don't know what you heard, but I might have said, have a great week, or have a great tweak, like it is on the slide. And I think people probably heard me say, have a great week, even though I was trying to say that one, because it's about 10,000 times more common in the English language, at least. So that's, we have our own language models in a sense, and we use them to disambiguate audio, and that's what we're recreating here. And so one way to do that is to use n-grams. So what is an n-gram? I think best illustrated by example. So we are going to the beach is a sentence that has 3 grams. And those are we are going to the, and to the beach. And so, they're just triples of words. Of course, you can have 4 grams, 5 grams. What an n-gram language model does is it counts all n-grams up to a certain order. And I won't go into math of how you turn that into probability, but you can see, I think, that all the elements are there to create a probabilistic model based off of n-grams. So once you do that, you'll have a language model based on a set of text that you can create. What you need to do is adapt the pre-trained language model. And that's because your word Kranky with a K, it's never been seen by that new language model. So it wouldn't know what probability to assign it. So you have to give it something. So here's the strategy. You build an in-domain model from a text data set from your application. What in-domain means, it just means it corresponds exactly to your application. It's something that you might build, and presumably it's going to be quite small. And then you also build an out-of-domain model on a large general English data set. This is going to give you coverage for the way that people speak. It's going to have hundreds of thousands of words, or at least tens of thousands of words in it. And then you're going to interpolate the two. And you get the best of both. You get the in-domain knowledge from your data set, and you get nice probabilities for over a large set of words. All right. So this is how you actually do it. So you're going to just add a few lines. I'm a Kranky geek. Many Kranky geeks live in San Francisco. We're going to add this to the corpus. And this gives it context for how, what kinds of words are going to precede and follow this expression. And it also just gives it a raw count of how often Kranky and geek follow each other. We're going to build the adapted language model. You're going to install a software package called SRLM. There's others out there. It's just a good one to get started with, and really a solid one overall. And you can run the n-gram count order function. So this is actually going to count the n-grams in your entire corpus and build a language model out of it. And finally, you interpolate this with a large language model. You could train on, for example, the Brown corpus, the Gutenberg corpus, Wikipedia. There's many choices out there. All right. And now you can recompose your decoding model with the new language model and the new lexicon. The reason you don't have to really change your acoustic model necessarily, there's a lot of, we adapt our acoustic models, but you don't really have to do it here, because if you think about the role of the acoustic model, it's to give you the probability of the sound condition on a phoneme, right? So like, if I say K, what are all the ways that could sound? That shouldn't matter if I add a new word. It shouldn't fundamentally change how a phoneme is pronounced. Okay, and so you can decode from there. This is the optional step. So in our use case, we have tens of thousands of custom words that our customers give us and want us to model. So if we had to go and manually add the pronunciation for each one of them, that would be a ton of work for us. There is a human element for verification, but essentially machine learning does the heavy lifting. So you can install Phonetosaurus. You can train this grapheme to phoneme model. So grapheme in English is, for the English language, just a letter, a grapheme. And then phoneme, we already saw, were these unambiguous sound representations. So it's going to look at the letters in a word and infer what the most likely pronunciation is. And these tend to be sort of 80 to 90% accurate, so they do a pretty good job. As a training data, you'll want to give it your CMU dictionary, which has over 100,000 words and their pronunciations. And then you can move on to the prediction phase. Phonetosaurus apply, you give it a word list, and here we go. It spits out the words we were looking for, actually here with the correct pronunciation. All right. The takeaways I hope you walk away with: to compete with off-the-shelf models, it's really advantageous to do domain adaptation. And to get the best results, it's a good idea, if you can, to keep the domain small and deploy a model for each domain. It might be one for each vertical, for example, sales support, or even finer grain, like what kind of sales is it, what kind of support. It could even be like we do for our large customers, they get their own language model. And this helps avoid word collisions with words that might occur frequently in other companies' corpora. And what you can do then, because there's a trade-off where the smaller the domain, you might think the less data you're going to have. So what you might want to do is use a mixture of corpora from different domains. So every domain gets its own model, but you're going to mix in many corpora from different domains inside and outside of it. That's it. Thank you.